Good morning. It is not good morning now. It is afternoon. It's now 1 p.m. Did you just wake up or what? Anyway, no problem. So I'll wait for some more people, then we can start the class, okay? So give 2-3 minutes. Okay, so Bikram is there. What happened? Why is present? Except you.
Maybe network problem.
Huh? I didn't listen. Okay, let us start. We are recording the video. So, so now in this session we are going to learn about Joule Thomson effect. Joule Thomson effect and Joule Thomson effect, or it is also called Joule Thomson cooling, or the experiment is Joule Thomson porous plug experiment. Okay, so uh, oh, so in the syllabus it is given like this. The syllabus it is given like free adiabatic expansion of a particle gas, or Joule Thomson porous plug experiment, and Joule Thomson cooling. Okay. So let us learn about this experiment. So here we have to learn something called throttling process. So what is a throttling process? So the throttling spelling you can see, you should remember this spelling, THROTTLING, throttling process. Okay. So what is the throttling process in Joule Thomson experiment? Okay, what is Joule Thomson experiment? We'll learn in a while. In Joule Thomson experiment, the porous plug provides a large number of very narrow paths for the gas molecules. Okay, so there is an arrangement for Joule Thomson experiment, and in that experiment there is a porous plug, and this porous plug provides a large number of very narrow paths for the gas molecules. Okay, so gas molecules actually flow from one region to the other region through a porous plug, and that porous, no, the name itself is porous. Porous means there are a lot of paths. okay, very narrow or small paths. Okay, while crossing these narrow orifices under high pressure, the gas molecules are pulled apart or are weighed down. So when these gas molecules pass through these narrow orifices, orifice means these narrow paths of the porous plug, and they move to the other portion. So they are pulled apart from one another. Pulled apart means they are just separated from one another. Okay, pulled apart are also called wear down. Okay, WIRE, wear down. And this particular process is known as the throttling process. So next time when we learn about throttling, in that case you have to recall this particular process. Okay, so in Joule Thomson porous plug experiment, so gas is allowed to pass from one region to other region, one place to another place through a very narrow porous plug which has very narrow paths. Okay, and while passing through this porous plug, the gas molecules are wired apart or pulled apart from one another. Okay, so this process is known as throttling process. Okay, so this throttling process will be required later. So remember throttling process. So what is Joule Thomson effect? So Joule Thomson effect also we have to learn. So what is Joule Thomson effect? And prove that Joule Thomson effect is a constant enthalpy process. What is the constant enthalpy process? We will learn it in the course of Joule Thomson experiment and effect. Okay. Okay. So notice what is Joule Thomson effect? So the change in temperature of a gas when it is allowed to expand through a narrow orifice or porous plug from a region of constant high pressure to a region of constant low pressure is called Joule Thomson effect. Okay, the change in uh, the change in temperature of a gas. Okay, when it is allowed to expand through a narrow orifice or porous plug from a region of constant high pressure to a region of constant low pressure is known as Joule Thomson effect. So let me try to annotate it. So this is suppose something called the porous plug. Okay, porous means there are a lot of small. Okay, how do I draw here? Okay, I cannot draw here. Sorry, it is a bit difficult to draw. Just give me a minute. I'm trying to draw something. Okay, suppose this rectangular shape is a porous plug. I mean, an arrangement, and there are a lot of narrow paths. Okay, narrow orifices, narrow like small paths. Okay, it is not completely opaque, but it has some small paths. Okay, it's a bit transparent. So now, if you allow a gas to pass through this arrangement, this plug, porous plug means it has very narrow paths. If now allow a gas to pass through such an arrangement, okay, from a region of low pressure, from a region of high pressure to a region of low pressure. Suppose you here on this side, suppose you have a pressure P1, and here on the other side of the porous plug you have a pressure P2. Okay, such that P1. So what are these pressure things we'll learn in a while. So very quickly we'll learn. P1 is greater than P2. Okay. When the gas is allowed to pass through the porous plug from a region of high pressure to a region of low pressure, then a type of cooling is generated. Okay. What is it? The change in temperature. Sorry, the change in temperature is what is observed. Change in temperature actually it results in cooling. So whatever be the temperature of the gas here, the temperature of the gas in the other part, in the other area will be smaller. Okay. So high pressure, low pressure, you allow the gas to pass through this porous plug. So after the gas passes through the porous plug, the temperature in the second region will be lower than temperature in the first region. Or in other words, there will be change in temperature. So T1 is greater than T2. So that means there will be a change in temperature. Okay. So that is the Joule Thomson effect. So Joule and Thomson they performed this experiment, and they found out that this gas actually there is a change in temperature of the gas when it flows from a region of high pressure to a region of low pressure through the porous plug. Okay. So now we have to understand mathematically. So how this change in temperature happens and under what conditions these things happen. Okay. Okay, so theory of Joule Thomson experiment. So let us learn about the theory of this experiment. So let us see what is the experiment setup and what is going on, how much pressure you have applied, and so consider consider a cylinder with non-conducting walls having a porous plug G. Okay, so G in the figure you can see this is the porous plug. It has non-conducting walls. Porous plug G having porous material like cotton, wool, silk. Okay, this silk, wool, cotton, they are already they are not very continuous materials. They are porous materials. Porous means so anything can like certain materials like gases or water liquid, they can actually pass through this porous materials. Okay, so some examples of such materials are the materials that we see around us, cotton, wool, silk, etc. Okay. Now consider two imaginary pistons A and B on either side of the plug. The porous plug are represented by G. On the other side of the porous plug, so we have a piston, an imaginary piston A, and here we have an imaginary piston B. Okay. On either side of the porous plug. So here there will be one mole of gas between the piston A and the porous plug having a volume V. Okay, so what is it? Let there be one mole of the gas between the piston A and the porous plug having a volume V. So let me annotate it here. So between this piston A, this is the piston A and this is the porous plug. This one is the porous plug. So it is assumed that a gas is placed. Okay, and that particular gas is having a volume of VA. Okay, that's what we are convinced. And okay, this is the initial condition of the setup. Okay, this is the initial condition of the experiment. So you place a gas between the piston and the porous plug. Okay, and the gas is having a volume of V. And the gas is one mole of the gas. Okay, only one mole of the gas is there. And let this gas be highly compressed to a pressure PA. Okay, so you can see this is PA. A pressure PA has been applied on the gas with the help of the piston A. Okay, let there be one mole of the gas between the piston A and the porous plug having a volume A. Okay, so and let the gas be highly compressed to a pressure a pressure PA has been applied to the gas. Okay, PA, and the pressure on the other side of the plug P. Okay, so this is the plug G, and on the other side here, a pressure has been applied. Suppose the pressure on the other side of the plug is PB. Okay, so due to this large difference in pressure, the gas flows through the pores. Okay, and becomes throttled and wired up. So have you understood the experimental element? So once again, consider two imaginary pistons A and piston B, and there is a porous plug between the two pistons. Okay, porous plug is represented by the letter G. Now let there be a gas between the piston A and porous plug G, such that the volume of the gas is V. Okay. Now this gas is suppose given a pressure very high, a high pressure of P. Okay. So this gas has been subjected to a pressure of P, and the pressure will be PA to the left of this porous plug, and suppose to the right of the porous plug we have another imaginary piston B, and suppose the pressure on that side of the porous plug is equal to PB. Here. So there is a difference of pressure. Why? Because of PA is already PA is actually greater than P. Okay, because the gas PA is highly compressed. Highly compressed means you push it highly with the help of the piston. Okay. So what will happen when pressure PA is greater than PB, or there is a difference in pressure? The gas on either side of the porous plug. Due to large difference of pressure, the gas flows through the pores and becomes throttled. Okay, the gas will. So this thing we have already done earlier. I'm just trying to do it again. So the gas passes through this porous plug and it becomes throttled or wired down. So what is throttling or wiring down? So because throttling means the molecules of the gas will move apart from one another. Okay. So and that is the throttling process. Okay. So earlier at the beginning of this particular class, we have learned about throttling. Okay. The molecules of the gas are throttled. Okay. So now, because of the gases are further apart from one another, okay, or the gas becomes throttled. Okay, so have you understood up to this? I hope you have understood up to this. So what is throttling? That's why we introduced throttling at the beginning of this class. Okay, and this experiment has been invented, so I hope you have understood. So now the question is, if the piston A is slowly moved inwards so as to keep the pressure constant as the gas escapes, the piston B will move slowly upwards to keep the pressure on the other side, pressure constant on the other side. Okay, so so if the pressure is PB, okay, so now this piston, okay, so we tend to maintain a constant pressures on either side of the porous plug. Okay, so in order to do that, in order to maintain constant pressures on either side of the porous plug, this piston has to be pressed or moved inward. Okay, moved inward very slowly. Okay, it should not be sudden. All of a sudden you come and you press the piston. No, it is not like this. The piston has to be moved very slowly. So why we need this? We need this in order to maintain a constant pressure PA on the gas. Okay. Now, if the piston moves very slowly, the outward and to keep the pressure. So now with this, if you move the piston very slowly, the piston on the other side will to B, or the piston B, or the pressure B, PB. Pressure PB is the pressure to which the piston B may be assumed to be circle, and therefore that particular pressure will also remain constant. Okay, so that means you maintain PA to be constant, so in that case PD will also be constant. But you have to be careful that in order to keep both PA and PB constant, you have to press the piston very, very slowly. Okay. Suppose now, finally, when the whole of the gases pass through the porous plug, you see now here the gas was between the piston A and the porous plug. And now here in this instance, what happens? The complete gas has passed through the porous plug. So the piston A is now in touch with the porous plug. Therefore, we can assume to be a scenario when all the gas has passed through the porous plug, and right now the gas is between the porous plug G and the piston B. Okay, so that is what it is written. Finally, all of the gas has passed through the porous plug. The pistons A and B will be in positions A and B. Okay, so the pistons A and B will have now a new position. Like earlier, see, this is the piston A, this is the piston B, and now all the gases pass through the porous plug. The pistons A and B are at different places. Okay, now consider that we have a volume of the gas which is VB. Under this current configuration, the volume of the gas is VB. Okay, earlier the volume of the gas. So what is VA? VA was the initial volume of the gas when the gas was between the piston A and the porous plug G. So after all the gases pass through the porous plug. So in that case, the gas will be now between the porous plug G and the piston B. Okay, so and in that case, suppose BB is the volume of the gas. Okay, so I hope we have understood the various pressure and volume terms. Okay, so pressures are PA, VA. Sorry, not PA, VA. Pressures PB, PA, PB, volume side. VA, VB. Okay, pressures are PA, PB, and volume side VA, VB. Okay, so I have understood up to this. What is the initial configuration and what is the final configuration? Okay. Okay, so then you see this come to this particular. Maybe I can remove this annotation. Now come to this particular part. Now, what is the work done by the piston A on the gas? We have to find the work done by the piston A on the gas. So that is directly given by work done is equal to PA V. Okay, that means the pressure so which you have applied on the which you have applied on the gas by the initial volume of the gas between the piston and the porous plug. That is the work done by the gas on the work done by the piston on the gas. Okay, you understood this because the piston is so you have used the piston. There the piston will work on the gas. Okay, work done by the piston on the gas, so which is PAV. Okay, what is the work done by the gas on the piston B? Work done by the gas on the piston is PV. So why it is so earlier it is work done by the piston on the gas, but in the second case it is work done by the gas on the piston. Since at A you are pushing the piston, therefore for A the piston will do a work on the gas. And now for the part B, the gas will expand. The gas is between piston A and the porous plug, and once the gas starts expanding through the porous plug, so the gas will expand and it will exert some force on the piston B. Okay, so have you understood this? So the gas, once it expands through the porous plug, okay, and to the right side of the porous plug there is the volume of the gas is VV. Okay, so once the gas expands, in that case the gas will exert a force on the piston B. That is why it is written as work done by the gas on the piston B. The work done is again PV multiplied by VV. Okay, so these work done things you have to remember. Once this is, okay, let me try to explain quickly. This is the piston, you have put the piston, and suppose this is the gas. Oh, what happened? That is not good. Wait a minute. This is the piston A, okay? The piston A is put towards the gas. Therefore, in this case, the piston will do a work on the gas, okay? But in the other case, this is the piston B, and the gas will come from the left, okay? Come from the left means come this way. And in this case, the gas will do a work on the piston. That is electricity work done by the gas on the piston B. Okay, that's why we have written like this. So in this case, the work done by the gas on the piston B is equal to PB. Okay. I hope you have understood this. Therefore, the net work done by the gas. What is the net work done by the gas? The net work done by the gas is PB minus PB. So this is correct. Therefore, the net work done by the gas is equal to PB minus PAV. Okay. So this quantity minus this quantity PB minus PAV, and that is the net work done by the gas. So now let us come to. So we will try to explain this from the first law of thermodynamics point of view. So what is the total internal energy of the molecules? Okay, so we are learning about internal energy. We have learned about this. So total internal energy of the molecules is equal to the sum of the kinetic energy of the molecules and the potential energy due to force of attraction or repulsion between them. Okay, so what is the total internal energy again? It is the summation of potential energy plus the kinetic energy. Okay, so let us come to internal energy consideration. Let UA be the internal energy of the molecules before passing through the porous plug, and UV be the total energy after passing through the porous plug. Okay, so UA, you see it once again. UA is the internal energy of the molecules before passing through the porous plug, and UV is the internal energy of the molecules after passing through the porous plug. Okay, therefore what is the change in energy, the change in internal energy is it is written UA minus UB, but I can write the change in internal energy to be UB minus UA. Okay, so why so in the book it is written UA minus UB, but I would like to write it as this UB minus UA. Okay, why? Because you see the net work done by the gas is given by PBV minus PAV. Okay, so it's up to you. The net work done by the gas may also be PAV minus PBV, but the B quantities, the B terms, I would like to keep positive. Okay, that's why this is the change in internal energy of the gas once it passes from the region A to the region B. Change in internal energy. Okay. Now, after all this, you just go to the first law of thermodynamics. Let me write it. So this is the first law of thermodynamics. Okay, remember heat up is equal to energy required to raise the one part of this energy is used to raise the internal energy, and other part is used in work done by the gas. Okay, that is the first law of thermodynamics. Okay, now this process is adiabatic. Okay, if this process is adiabatic, this Joule Thomson experiment. Okay, remember we are still learning Joule Thomson experiment. If this is adiabatic, so we can write dq equal to 0, because in an adiabatic process no heat is allowed to enter or leave a thermodynamic system. Du is dq is 0, so du plus du is ub minus ua, dw is pb minus pav. Okay, so this is what we get. So dq is equal to du plus dw. So adiabatic process dq is 0, du is ub minus ua plus dw is pb minus pav. So rewrite this equation. So all the b quantities you write together. I mean all a quantities we write together. First, okay, let me write a quantities ua plus pava equal to, since the process is adiabatic, heat is 0, the b quantities you write together. Okay, so now you see we get the equation like this. So ua plus pva, ub plus pbb, okay, which is constant. Okay, that means this quantity is constant, because if a and b all summations are constant, it means this is a constant. This both summations on either side are constant. So right now, you remember what is the expression for enthalpy? So do you remember that this is the expression for enthalpy? Enthalpy is generally given by this capital H, which is equal to U plus PV. So U means U stands for internal energy, and P stands for pressure, and V stands for volume. So enthalpy is equal to H is equal to U plus PV. Okay. So now, so H, so therefore, okay, how we can write it? Let me write it like this: UA plus PAV equal to U plus PDV. So that we can get HA equal to enthalpy of this part and HB is the enthalpy of the other part. Okay? That means H is a constant quantity. Since it is constant, therefore, although the process has changed, but the enthalpy has not changed. H is a constant quantity. Or in other words, enthalpy, H stands for enthalpy. Enthalpy is constant in Joule Thomson's Porous Plug experiment. Enthalpy is a constant quantity in Joule Thomson's Porous Plug experiment. Okay. Therefore, the Joule Thomson experiment is also known as it's like constant enthalpy process. Okay. Joule Thomson experiment is also a constant enthalpy process. Why? Because just now by mathematical derivations we have shown that the total enthalpy remains constant. Okay. Or enthalpy constant is also sometimes written as isenthalpic process. Isenthalpic, I-S-E-N, isenthalpic. So this process is also sometimes known as isenthalpic process. Okay. Okay, so Joule Thomson effect. So it may be like a multiple choice question in exam. So which of the following processes is Joule Thomson's expansion of gases? So it may be, you may be given 4 options, like it's a like isothermal process, or it's an isobaric process, it's an like isochoric process, or it's an isenthalpic process. So in that case, your answer should be Joule Thomson's Porous Plug experiment is an isenthalpic process. Okay, or a constant enthalpy process. Okay, come to the end of this part, and then in the next part we will show about the cooling process. How Joule Thomson expansion. So this is a given question. What is Joule Thomson effect that we have done rapid expansion for changing temperature during Joule Thomson effect? So this next target is to find an expression for change in temperature with Joule Thomson effect. Okay, so if the change in temperature expression will find, and we will eventually show that Joule Thomson's effect results in cooling. Cooling when the gas passes from a region of high pressure to a region of low pressure through a porous slab. Okay, so there is a change in temperature after the expansion of the gas. Okay, and this how this temperature changes, that particular thing we will be learning in the next class. Okay, so it's all for today. So we have learned about what is throttling process, what is Joule Thomson's experiment, and we have also showed that Joule Thomson's experiment is a constant enthalpic process, or the enthalpy remains constant in this process. Okay. So anyway, so in the next class and in the next class, I will continue this topic. So we will learn about how this cooling happens. Okay, mathematically we will learn cooling, how Joule Thomson's effect gives rise to cooling. Okay. Anyway, so I think